Hello, everyone. This is Safa, and today we're going to talk about generative adversarial networks. It is a very popular paper. There are like thousands of variations now of it. This was written by Ian J. Goodfellow, and yeah, the guy actually had the idea in a bar, apparently. So firstly, we're going to try to understand the paper together. So yeah, let's delve in. We propose a new framework for estimating generative models via an adversarial process in which we simultaneously train two models, a generative model and a generative model that captures the data distribution and a discriminative model that estimates the probability that a sample came from the training data rather than G. Okay, so basically, there are two models that we need to train. There is a generator and there is discriminator. The goal of the generator is basically to capture the data distribution. We want it without seeing the data itself. We wanted to capture like to basically, yeah, to capture the data distribution. We wanted to be as close to the data distribution as possible. And the discriminator's job is to be able to tell if the data that it is coming across is from the training data or is it the data that is generated by the generator, which is basically the fake data. The training procedure for G is to maximize the probability of D making a mistake. So they are, there's a reason why they're called adversarial nets. They're called adversarial nets because their objectives are different. The generator wants to fool the discriminator into believing that whatever data it is generating is actually from the training data distribution. In order to do that, it is going to capture the data distribution. So, in the space of the arbitrary functions G and D, a unique solution exists with G recovering the training data distribution and D equal to half everywhere. There's a unique solution, the optimal solution, where G basically, if you're saying that G recovers the data distribution completely, and D is equal to half everywhere. What that means is is basically outputting a probability, right? That the data is from the real distribution or the training data distribution. So it is half. If well, basically that means is that discriminator is not really sure, which means that generator has been successfully able to produce data that discriminator cannot really tell if it's from the real distribution or the fake distribution, real data or the fake data. In the case where G and D are defined by multi-layer perceptrons, the entire system can be trained with backpropagation. What they are trying to say is that we're not using Markov chains, we're not using complicated inference methods. What we are doing is we're going to use backpropagation to completely capture and train G and D. And experiments demonstrate the potential of the framework through qualitative and quantitative evaluation of the generated samples. The promise of deep learning that represent probability distribution over the kinds of data encountered in artificial intelligence applications. Okay, so this is not that important. In the proposed adversarial net framework, the generative model is pitted against an adversary, a discriminative model that learns to determine whether a sample is from the model distribution or the data distribution. That is something that we already discussed. So this is not that important. Related network, well, related work. So there were Boltzmann machines, deep belief networks. A lot of that is not used today. What is used, however, and Markov chains as well, but what is used, however, is this. This is super important. Variational autoencoders that are still used. I'm going to do another video on variational autoencoders, but for now, this is one other. Unlike generative adversarial networks, variational autoencoders pair a differentiable generator network with a second neural network. There are two neural networks used in variational autoencoder as well. In VAE, though, you are first encoding and then decoding the information through those two networks. One network is used for encoding the information. The second network is used to decode the information. And I will do a more detailed video on that again. So GANs require differentiation through the visible units, and this cannot Unlike generative adversarial networks, the second network is a way is in a VAE is a recognition model that performs approximate inference. So GANs require differentiation through the visible units and thus cannot model discrete data, while VAEs require differentiation through the hidden units and thus cannot have discrete latent variables. So basically, you know what visible units are. Visible units are what you can see, like the input and the output. Those are visible units, and anything in between are the hidden units. And what they're saying is that GANs cannot model discrete data because it goes all the way back, propagates all the way to the last layer, to the visible layer. So yeah, like it cannot model the discrete data, while VAs require differentiation through the hidden units. So in the hidden units you cannot have discrete latent variables. Latent variables are the values that are here in the hidden units. And okay. So now we're going to discuss specification of the learning process is different, predictability So what they're saying is that we are going to predictability minimization is described as an optimization problem with an objective function to be minimized, and learning approaches the minimum of the objective function. GANs are based on a minimax game rather than an optimization problem and have a value function that one agent seeks to maximize and others seek to minimize. So basically, predictability minimization is when we have objective functions and we are taking steps. The objective, we have cost function and we want to minimize the cost, right? But here, this is a minimax game. What that means is that you're basically training one network, then you're like, and then you are using that value and you're training another network uh, based on that value. Like you keep, it's a game between two adversaries rather than one objective function. So there are two values for the both neural networks, and you have to train them together. GANs are based on a minimax game rather than an optimization problem and have a value function that one agent seeks to maximize and other seeks to minimize. Yeah. So the value function that one agent seeks to maximize and the other seeks to minimize. So the value function we're going to discuss now. This is basically the value function that they're talking about. So the value is D stands for discriminator, G stands for generator, and the purpose of the discriminator is basically to maximize this value. So how it's going to maximize this value is, this is for the real data. When it's the real data, the discriminator wants to maximize the expectation, and when it's a fake data, then discriminator wants to minimize the expectation. This is the prior on the noise distribution, and yeah, and when discriminator is trying to do all of that, the generator is trying to minimize of like whatever this is going to output first, whatever attempts discriminator are going to make to maximize this value. The generator's goal is to minimize this value, so it's going to take an adversarial step and try to update its values to minimize this whole value. So the theoretical results, the generator GM defines a probability distribution PG as the distribution of the samples obtained when Z is around PZ. And therefore, we would like algorithm 1 to converge to a good estimator of P data if given enough capacity and the generator G. Sorry, you guys give me a minute. So there is a generator G defines a probability distribution PG as the distribution of the samples obtained when Z is around PZ. Therefore, we would like algorithm 1 to converge to a good estimator of P data if given enough capacity and training time. The result of the section are done in non-parametric settings. We represent a model with infinite capacity by studying convergence. This is not that important. So we will discuss this now. What is this? So this is the noise. Basically, the generative adversarial nets are that's this. So the generative adversarial nets are trained by simultaneously updating the discriminative function. Just a second. The generative adversarial nets are trained by simultaneously updating the discriminative distribution D. D is the distribution of the discriminator. So that it discriminates between samples from the data generating distribution black and the generative distribution PG. So this is PG. This is the distribution, or the black dots represent the distribution of the original data, and this is the discriminators probabilities. The lower horizontal line is the domain from which Z is sampled. So Z is sampled, the noise is sampled from certain distribution. You can tell which. For instance, we're going to take, in this case, it's uniform. So from uniform distribution, we have noise. The horizontal line above is part of the domain of X. So basically, this is what the generator is doing. Wait. So, so there's a generator here which is taking the noise and transforming it into X, and then that is being passed to the discriminator. The upward arrow shows how the mapping X is equal to G of Z imposes the non-uniform distribution PG on transformed samples. G contracts in regions of high density and expands in regions of low density. Consider an adversarial pair near convergence. PG is similar to P data and D is partially accurate classifier. In the inner loop of the algorithm, D is trained to discriminate samples from data. So basically, this is how it's calculating the probability of. So after several steps of training, if G and D have enough capacity, they will reach a point which both cannot improve because PG is equal to P data, which is like both of these probabilities are half and half. So basically, generator and discriminator have both come to that ideal point that we discussed before. So the discriminator is unable to differentiate between the two distributions, as I said, it's half. It does not really know which image is from which distribution. So this is the algorithm basically. Minimal stochastic gradient descent, training of generative adversarial nets. The number of steps to apply to the discriminator K is a hyperparameter. If we use K is equal to 1, the least expensive option in our experiments. Okay, so for number of training iterations do, for K steps do. So K steps are basically what you're trying to do is you are going to train a discriminator a little, and then you're going to train the generator. You should not train the discriminator a lot or the generator a lot. Like you shouldn't first train the discriminator fully, because if you do that, then when you are trying to input the generated images, discriminator is going to say no to each image, and it would not back propagate well. So what you want to do is you want to take, for K steps, you first train the discriminator. Sample mini batch of M noise samples from noise prior PG of Z. This could be like you could choose any prior distribution. Here they have chosen, in the paper they've chosen uniform. Sample mini batch of M samples from data generating distribution. So you have two types of samples. You have noise samples and you have samples from the data generating distribution. Update the discriminator by ascending its stochastic gradient. So basically what you want to do is, as we discussed in the value function, you are going to ascend the stochastic gradient for discriminator because you're trying to maximize that value. So you're basically trying to maximize this value, right? So you're going to ascend the stochastic gradient for, you take this is this, all of these. you're taking m examples and you're trying to maximize the discriminator's ability to you're taking the expectation here, basically the summation. You're taking the you're maximizing the discriminator's ability to tell if the data is from the real distribution or the fake distribution. And you're trying to minimize this by doing 1 minus d of g of z. G of z is the generated image. So let's just say d of x dash, or so you're trying to minimize this. Uh, and once you've done that, what you are going to do is you're going to sample many batch of M noise samples again, and you're going to update the generator by descending its stochastic gradient. Now, this is the update step. You're going to back propagate to the generator, and as we saw in this value function as well. So the first value here is for the discriminator, and the second value here is for the generator. Since in the first value there's no generator, so we don't really need it. So for the updation here, we only need to maximize this. We're trying to maximize this while the discriminator is trying to minimize this, right? So the gradient-based updates can use any standard gradient-based learning rule. We used momentum in our experiment. Okay. So we first consider the optimal discriminator. Now they're trying to delve into a lot of maths. What they're trying to see that, if we first consider the optimal discriminator D for any given generator G for G fixed, the optimal discriminator D is this. So you're taking a proposition, then the proof is, they're trying to prove it mathematically as well. And they're just trying to prove what they already mentioned. I'm not going to go into that. If you want to go into that, I can attach a video. There's another video that explains the paper well as well. So if you guys want to go through that, you can. If GND have enough capacity and each step of algorithm 1, the discriminator is allowed to reach its optimum given G, and PG is updated. So PG is basically remember the green line that we talked about? So basically we wanted to capture the black dots, right? We wanted to capture the training data distribution. So if G and D have enough capacity, and at each step of algorithm 1, the discriminator is allowed to reach its optimum given G. And PG is updated so as to improve the criteria. So at each step of one, for K steps, you're running the discriminator, you're training the discriminator, and then you are you're back propagating the error, and you're training the generator. So basically, what you're trying to do is you're trying to update PG, you're trying to bring it as close to the data distribution as possible, right? So this value here, to the left, if we go to the left, it's as you can see, the discriminators, this value is increasing towards the left. So what you want to do is you want your PG to also move towards left, because that's where the discriminator is leading it. And eventually what you want is, this is when the discriminator has a probability of half for every new encountered data point, and this is basically the data distribution is captured. And by the way, you use logs and all of that because the mathematics is easier if you're using the logs, and it helps with the chain rule as well. Like the mathematics is easier basically with the logs. What else? What else? Okay, so they've experimented with MNIST. They have used Toronto Face database as well and CFAR, and they have some results. They have some advantages and disadvantages as well. We will read through them. Let's read through them. So this new framework comes with advantages and disadvantages relative to the previous modeling frameworks. The disadvantages are primarily that there's no explicit representation of P of G effects, and that D must be synchronized well with G during training. In particular, G must not be trained too much without updating D in order to avoid the Helvetica scenario in which G collapses too many values of Z to the same value effects. Okay, now this they are talking about modal collapse here. We will let's let's talk about that. And I think I'll do another video later as well about how to avoid the modal collapse with some other variants of GAN. Um, so yeah. So the advantages are primarily there is no explicit representation of P of G of X, and that D must be synchronized with. So what they're trying to say is that if you're training G too much, if you have to synchronize them well enough, like you have to choose K carefully, uh, because if you do not do that, what can happen is that D must be synchronized well with G during training. In particular, G must not be trained too much without updating X. If we train G too much, then it will be able to easily fool discriminator by providing the same. If it knows that discriminator on this value is not able to tell if the data point is fake or real, then one way of fooling the discriminator is to constantly provide the same data point because it knows that discriminator is not will be confused. So that is called modal collapse, MODAL. Guys, excuse my writing. So yeah, you guys get it. Yeah, you know how collapse is spelled, right? So yeah, it collapses too many values to the. So basically, we want to avoid that. For what are there much as a negative chains of Boltzmann machines where we get. We're not going to talk about Boltzmann machines. The advantages are that Markov chains are never needed. Okay, the so this is another interesting thing. Markov chains are never needed. Before that, they were needed, and apparently there are papers afterwards as well that use Markov chains along with the generative like they try to improve the GANs through Markov chains, and apparently the whole objective was to avoid the Markov chains and complicated mathematical models. Only backprop is to be used to obtain gradients. Sorry. So only backprop is used to obtain gradients. No inference is needed. The aforementioned, so these are the advantages. The aforementioned advantages are primarily computational. Adversarial models, so interesting. Adversarial models may also gain from statistical advantage from the generated network not being updated directly with data examples, but only with gradients flowing through the discriminator. This means that components of the input are not copied directly into the generator's parameters, but only with gradients flowing through the. So statistical advantages that it's updating directly the generator. Okay, so basically what they're trying to say is that the generator is not able to see the real data. So the most awesome thing about their paper is that the generator is being trained primarily by just updating the weights, by just gradient flowing through the discriminator. This means that the components of the input are not copied directly into the generator's parameters. Another advantage of adversarial network is that they may represent very sharp, even degenerate distributions, while methods based on Markov chains require that the distribution be somewhat blurry in order for the chains to be able to mix between modes. Okay, well, okay, well. So we're going to the conclusion of future work now. This framework admits many straightforward. Basically, they have shown here, they have visualization of samples from model. Rightmost column shows the nearest training examples of the neighboring example in order to demonstrate that a model has not memorized the training set. Samples are fair random draws, not cherry picked. Unlike most of the visualizations of degenerative models, these images show actual samples from the model distributions, not conditional means given samples of hidden units. Moreover, these samples are uncorrelated because the sampling process does not depend on Markov chain mixing. Uncorrelated Okay. So basically, they're trying to show that digits obtained by linearly interpolating between coordinates in z space of the. So apparently, they were doing interpolation at that time as well. Um, yeah, so they were basically trying to show that they're performing better than others on these models, MNIST, TFDC5, and apparently they were doing interpolation at that time as well, and these are some other potential future works that they mentioned, and most of this future work has actually happened. A conditional derivative model P of x of c can be obtained by adding c as both as input to both g and d. Learned approximate inference can be performed by training an auxiliary network to predict z given x. Apparently, their inferences have also happened. One can approximately model all conditionals where S is a subset of indices of X by training a family of conditional models that share parameters. Essentially, one can use adversarial networks to implement a stochastic extension of. Well, these are the semi-supervised learning and conditional models. I've come across those before. So yes, so these are the future works. I hope we have been able to understand the paper. Thank you very much. And I will be coding a simple GAN or on a TensorFlow. So if you want to see that, if you want to follow that, you guys can check my other video. Thank you.